How's it going, guys? I'm Michael Hyde, and today we'll be going over Lab 4 oscillation. Today we'll be learning about systemic energy, springs, and waves in the form of an experiment. Now, this lab will be discussing the internal transfer of energy through both kinetic and potential energy, for which we have to know the energy principle formula. This is given as E final minus E initial, or delta E, equal to the work done plus Q, which is the thermal. Now, Q will be 0 since there is no change in the thermal being recorded. And we also have to realize that delta E is equal to K plus U, where K, kinetic energy, increases and U, potential energy, decreases proportionally, which we will find out later. Now, for non-constant work, which work is force times the distance traveled, we will have to take the integral, which is R initial to R final, and we see that this comes out to 1/2 ks squared when looking at the spring constant, which is K. This is the equation that we will use for potential energy for this problem. Now, the experiment that we are doing is we will be pushing a mass on a spring to see the oscillation in both the x and the y direction. Given this initial velocity, the push, we will have to observe the relationship between acceleration, deceleration, and the shift in energy. One thing to notice that we'll be talking about later is that the x position graph on the left and the y position graph on the right, one is a sine wave and one is a cosine wave, which leads to a phase shift we will later get into. In terms of our energy, we have to realize what the ideal image of the energy principle is, where no additional force into the system is given beyond the initial push. On the right, we see this graph, however well it's drawn, and we can see that K begins to decrease after the first peak, and at that same exact time t, US begins to increase. We see that they are at equal positions along the graph, which will lead to this delta E, which is the relationship between these two, where it meets at one flat line, one constant flat line, since they are directly inverse. For a period comparison, we had to find the oscillation period for both our y and x values. To do so, we have to look at the peak y and x values given above and find the average of the time difference between each peak. This leads to our final value of a period of 1.62 seconds for our y values and a period of 1.65 seconds for our x values. The most important thing to note, which I mentioned earlier, is that the phase shift is because of the similarity between these two values. With a same period, but different starting points, they end up lining up to where while y is at its peak, x is at its equilibrium, seen here, and vice versa, where x is at its peak and y is at its equilibrium. And this will continue throughout the entire full period of this oscillation. Now, for a bit of a conclusion, we have to remember two things. First is that the energy principle, where kinetic and potential are directly related. Going back over this equation, we have delta E equal to W plus Q, and that kinetic increases as potential decreases. And second is that a spring and a pendulum have comparable oscillation. This oscillation that I mentioned is the x value due to the swinging or the pendulum of this spring, which has a tension T, and the spring itself, which affects the y direction, which oscillates. These create two different waves, but two very similar distances, and it's quite an interesting connection. Thank you.